There is an amazing invention that is very common in our lives, the strain gauge, particularly the electronic scale. Let's delve into the working principle of electronic scales. Unlike mechanical scales, electronic scales lack a spring mechanism. Instead, they rely on a small structure to measure weight. When we step onto the tray of an electronic scale, a component called the strain sensor undergoes stretching and deformation. Upon stepping off, it returns to its original shape. The strain sensor features several golden flakes on its surface, which constitute the core of the electronic scale, the strain gauge. The structure of the strain gauge is delicate. Its middle layer consists of a conductive copper grid, while the lower layer comprises a thin plastic film. The upper layer serves to encapsulate and protect the conductive copper in the middle. The conductive copper foil has 2 feet that act as welding points, surrounded by tiny markers. During installation, these markers aid in alignment. The critical part of the strain gauge is the conductive copper grid in the middle, produced through photolithography. This grid shape maximizes axial deformation while minimizing lateral deformation. When pressure is applied to the electronic scale, the strain gauge deforms, causing a change in its resistance. This alteration generates an electrical signal, which is then integrated into a circuit known as a Wheatstone bridge. The bridge consists of 4 resistors arranged in a diamond shape, with each connected to a strain gauge. As the resistance of one or more strain gauges changes due to deformation, the circuit's balance is disrupted, resulting in a small voltage. Since this output voltage is too minuscule for direct measurement, engineers often add amplifiers to boost it to a level that subsequent electronic components can accurately process. Following this, engineers use an analog-to-digital converter, ADC, to convert the voltage signal into a digital format. This entire process digitizes the analog force exerted on the electronic scale, yielding discrete digital values. These values can then be further processed by digital circuits. The electronic components employed include microcontrollers or digital signal processors. After filtering, compensation, and calculation, our weight is displayed on the LCD panel. This constitutes the working principle of electronic scales. Now let's shift our focus from these complex analog and digital signals to the strain gauge itself. It's not just limited to electronic scales. Its ingenious design finds applications everywhere in our daily lives. For instance, by adhering it to a material's surface, we can measure its hardness. Additionally, when placed in key bridge structures, engineers can continuously monitor and manage load changes. Furthermore, connecting the strain gauge to a high-speed rotating machine allows it to output crucial data, enabling engineers to optimize equipment performance and extend its service life.